2, 1.
Go. Okay, thank you. Thanks for coming and braving the weather. I believe this has been televised, so I think at the end of the lecture, with questions, do we have to move a mic around? We probably do, right, to get to questions? Okay. So at the end, when we have questions, just wait until the mic comes around so those online can, hear the question. Okay. So it's a great pleasure to introduce our VIP speaker today, Christian Jakob, who's from Monash University, and he's from the Department of, let me see if I get this right, Department of Earth, Atmosphere and Environment. Did I get that right?
Good work.
Well, that's a good guess, wasn't it?
Good work.
And the professor at Monash University, he also was a director of a fairly large kind of consortium project on climate. I forget what it was called, but I was connected to it. And he's now also involved in a climate extremes activity in Australia. Christian tells me he started exactly the same day as Joao at ECMWF, some many years ago. So they spent a number of years at ECMWF dealing with the issues of trying to make the best weather forecast model on the planet. And they did it. So they and it's all been downhill since they left, is it right?
No, right.
No, okay, all right. Christian has also been until recently, Christian's sort of been the chair of the WIGNI, the International WIGNI activity, which is a working group of numerical experimentation. It's where all the major modelling centres, where the modelling centres get together to kind of compare notes and kind of scratch their head as why certain things don't work and why certain things do work. He was also until recently, the chair or co-chair maybe of the WCRP's Modelling Advisory Council, right? And I expect he's going to be involved in bigger things in WMO in terms of advisory. It's coming up. Published more than 800 scientific papers and contributed to development of several major weather and climate models across the globe. He's kind of an expert on convection, and some of this talk will kind of touch a little bit on convection, but it goes a lot beyond that. It's very appropriate he's going to talk about rain because, we just got dumped upon, and he's going to probably explain why we get so much rain, right? No?
Yes.
Okay, right. And how it's going to change in the future?
No.
No, okay, he's not going to do that. So it's a great pleasure to introduce our VIP speaker, Christian.
Thanks, Graham. It's great fun to be here. It's my first time at JPL. Not my first time at Graham's house, but my first time at JPL. So thanks, everybody, for braving the rain, which I will be blamed for. Joao already did it. He said, I brought the rain. That's fine. I can handle that. We're going to talk a lot about rain today, but in a very old, talking about a very old problem, actually. And yes, whilst the talk is 90% observations, which will make you at JPL happy because most of them are taken from space. Actually, all of them are taken from space. It wasn't a requirement, but it turns out that way. It's motivated by modeling, actually. It's motivated by me trying to make, in Australia, we're currently working with the Met Office model. And like every climate model, that has errors in precipitation. And one of the biggest errors in precipitation that almost every model has, rains too much in the tropics. Could be an observational issue. I don't want to blame the observations outright, but there are issues with observations of precipitation, of course, especially over the oceans. But every model seems to overestimate precipitation in the tropics. So I spent 2 years with a postdoc trying to reduce this error, and we played with the deep convection scheme as one does, because that's the sort of first idea one has, change something in the convection, and we couldn't make it go away. So then I thought, well, maybe it's something else. And so this sort of motivated this work. The other thing that I always like to tell at the beginning of this talk is a lot of science gets done out of anger, because you get angry with what other people are doing. You say, this is just, what are they doing? This is ridiculous. And you say, I have to prove that it's ridiculous. And so this is one of those pieces of work is in here. I'll tell you which one it is. So let's get stuck into it. It's a rather nebulous title, but it's an old topic. It's a topic that's often associated with a paradigm or theory of radiative-convective equilibrium, which I will use quite a bit. The term, although I prefer the term balance, but the balance I'm going to talk about is between radiation and convection. And it's a very old idea that globally averaged, the Earth's energy drives the Earth's precipitation, because precipitation is associated with the release of energy. And if you globally average, the radiative cooling of the atmosphere needs to be in balance with the latent heating from precipitation plus any addition from heat from the surface, which is usually the sensible heat flux. And that has to be true in a long-term average and in a long-term global average. Okay? Manabe and Strickler in the 60s built a very simple globally averaged model, and they showed not only is this a sensible concept for energy balance of the planet or of the atmosphere, and specifically not the planet but the atmosphere, but it also helps explain the vertical structure of temperature. And this highlights the fundamental importance of convection in this in the climate, in that if you allow nothing but radiation to act on the atmosphere, you get this sort of lapse rate. And if you compare that to what's observed, it's way too steep. It doesn't match anything that we observe on the real Earth. And then they say, oh, well, maybe that's because we don't have any turbulent, no overturning in this model, only radiation. So let's put overturning in and let's make it dry. And if you do that, you get this sort of middle profile here. And that's closer to the observations, but still not anything like the observations. And the only way you can make your vertical, globally or tropically average profile look like the observations is to invoke a moist overturning, which is tropical convection. And if you do that, then you get the right lapse rate of about 6.5 degrees per kilometer or something like that. So this shows that fundamentally convection is involved in setting this lapse rate whilst it's also producing the precipitation or the latent heating that balances the radiative cooling. So that was a rather interesting finding. This concept has been around for a very long time, well before Manabe and Strickler, but it has had sort of a revival, and this is where the anger comes from. It had sort of a revival very, very recently after laying dormant for decades in the modeling community. And it started with a paper by Chris Bretherton, where people took what's called a cloud resolving model, so 1 kilometer-ish resolution, and they ran these simulations of radiative-convective equilibrium, which they forced the model to be in this equilibrium. And they found that on scales of this is about 500 by 500 kilometers. When they run the model, the equilibrium in rainfall looks something like this. So you get this blob of rainfall in the model, and the rest of the model is completely dry, and in water vapor it looks something like this. So this blob of rainfall sits in a moist spot, and the rest of the atmosphere around is very dry. People get excited about this, and since 2005, the literature hasn't stopped obsessing about this. And I mean obsessing. It's an obsession of people. The whole industry, there's now a MIP, of course, Model Intercomparison Project for RCE. There has to be a MIP if it's popular. And this is simulations that are done with global models, which are run in this very funky RCE state. So they don't rotate. The insolation is the same everywhere on the planet. The SST is the same everywhere on the planet. And again, people find that depending a bit on the surface temperature, models tend to make these blobs of rainfall, with the rest of the planet being very dry. And there's theories on how this works. It invokes radiative processes driving the organization. And we've gotten to the point where people think that tropical cyclones form this way. That actually tropical cyclones are made by radiation, by radiative processes, by feedbacks. Yes, Kerry Manuel and others have. If you make this RCE rotate, you get a tropical cyclone. And so therefore, it must be true. So we'll come back and criticize this a little from observations. So this is where modelers get upset about other modelers and then have to turn to observations to actually show whether this can possibly be true. And then the final reason, this final piece of motivation is that we've known for quite some time that if you run climate models into the future, the rainfall, so the water vapor changes roughly with the Clausius-Clapeyron equation. So as the planet gets warmer, more water vapor is in the atmosphere, and the extra water vapor goes roughly with the Clausius-Clapeyron relationship, but the rainfall does not. The rainfall only, so this is about 6 or 7% per degree warming. But the rainfall, and this is just from a paper from Allen and Ingram, which use a whole different set of models, the rainfall only increases with about 3% per degree. And that tells you that the water vapor can't be the constraint on the rainfall. There must be something else that actually acts, and that's something else, again, is an energetic constraint, is this radiative-convective equilibrium. It doesn't matter how much more water vapor you could potentially rain out. What matters is how much does this water vapor, the extra water vapor, change the radiative cooling of the atmosphere? Because that's what needs to be balanced by latent heating in the end, or sensible heat fluxes, but they are, as we will show, a small term. So given all this motivation, we had a few questions, and the one good thing about being a modeler, I think, is that you'd like to do things quantitatively, not just qualitatively. You don't just want to draw a picture. You actually want to calculate numbers. And so the questions we had at the start of what I'm going to show, of the study we did, is can we quantify, we must have observations. It's 2018, I thought, or 2017 when we started. Surely we have observations to look at this problem of radiative cooling of the atmosphere versus latent heating from observations. So question number one, is there some way we can quantify this? Once we quantified it, can we actually understand the mechanisms behind this? How do different regions of the system interact with each other to establish this radiative-convective equilibrium? And then importantly for my anger part, to calm my anger, what are the spatial and temporal scales in the real atmosphere at which we find this? Right? Is it 500 kilometers? Because that's what these cloud-resolving modelers tend to use. So the question is 500 kilometers a sensible scale to actually invoke this paradigm of radiative-convective balance? The obsession in the community is about this organization of convection. So my next question is, can we from observations say something about organized convection and how organized convection plays a role in establishing this equilibrium? Or does it or doesn't it? Is it important? Because in the models, it's it, right? That's it. It's the organized convection is the thing that fascinates everybody. And then right at the end, I'll talk a little bit about climate model errors because there's some fascinating things that have come out of that and what are the implications for precipitation. So let's start. Here's my introduction to the problem from observations. So we need three pieces of information to do this. We need the radiative cooling of the atmosphere, and that's not OLR. You guys all probably know this, but you'd be surprised how many people think they can estimate the radiative cooling of the atmosphere by looking at top of the atmosphere radiation. And this is why no one's really done it, because the atmospheric cooling is, of course, the top minus the bottom. So you need estimates of the top of the atmosphere radiation. We are pretty good at this. So in this study, we use series estimates, daily estimates, which is the EBA sort of filled in version of the series data set. They've also do estimates of the surface radiation, which you need, because the radiative cooling is of the column is the top minus the bottom. And if you put the two together, this is what the atmospheric radiative cooling of the planet looks like averaged over 9 years, 2001 to 2009, is what we use in this study. All right? So you see there's actually the largest cooling on the subtropical oceans in the Arctic and the least cooling in the tropics. This is rainfall. We use GPCP over here. And the sensible heat flux we treat a bit like a stepchild. So we just use a poor reanalysis sort of product, rather than trying to get it from observations directly. And we can kind of do this because it's the smallest term. We are interested in the tropics, so everything I'm going to show you is going to be relevant, is going to be calculated in the region from 30 north to 30 south. So tropics is used in a very loose sense here, because as you all know, 30 north to 30 south contains a large fraction of the subtropics as well, which will become very important. If we calculate the terms that we are interested in, there's three, and average them over the tropics and over 9 years, here are the numbers. So the radiative cooling is 104.5 watts per meter square. The precipitation converted into energy units is 85, and the sensible heat flux is 22.5. If you add them all up, you get a residual of about 3 watts per meter square, which is sort of contains everything. It contains transport of energy out of the tropics, which we know happens in the atmosphere. But it contains also any potential measurement error there might be in any of them, right? It's all lumped together in this residual here. Oops. But what's kind of remarkable is that the residual is actually relatively small compared to the terms. It's about 3% or so. Land and ocean. This is everything. It's land and ocean together. So from this, we conclude in the long term, over the tropics as defined 30 north to 30 south. First important conclusion. We can see that there's a very good balance between radiation, precipitation, and sensible heat flux. Okay, so this RCE paradigm seems to be working okay as a good first order approximation if we average over the whole tropics and over a long period of time, 10 years.
But how about if you average locally?
Well, that'll be the rest of the talk. So just hang in there. Well, you can already see, those of you who pay attention in talks, you can already see that, you can already answer that question. It can't possibly be true locally. And why not? Because the regions where it rains the most are the regions where it cools the least. Well, that's... Yes, indeed, they will. So we can already see locally this can't possibly be true. Another way of displaying this is one of my favorite diagrams. You better like it. So what we do is, I like two-dimensional histograms these days because they show nice relationships between variables. So this is a two-dimensional histogram. All I did is I took these maps and I take each grid point as an entry into this frequency, this two-dimensional frequency distribution. And I just ask how many points in this climatological map have a combination of this rainfall on the x-axis and this radiative cooling on the y-axis. And what we see is most points in the tropics fall into the group down here, where we have very little rain or no rain and very large cooling. And then we have this diagonal populated. As we go to more rain, the cooling reduces, actually. So there's anti-radiative-convective equilibrium, if you wish. It's the opposite. And here, because I need to wake you up at this point of the talk, here's audience participation. There's a really cool area here where we see there's not much rain on Earth, but it also doesn't cool very much radiatively. It's sort of a minimum in the cooling and a minimum in the rainfall. So the question, and there's no prize because I didn't bring anything. I wanted to raid Graham's wine cellar, but it wasn't impressive enough to go and raid. The question is, which area in the tropics is this? What's this? You know, because I've already shown you the slides, so you shut up. All right, is anybody? Yes, that's what I thought. Completely wrong. Anybody else? It's true that I thought this. So when I made this plot, I said, oh, I know where that is. That's the cirrus outflow regions, right? So we reduce the cooling, but it doesn't rain anymore because we're at the edge of the... No. No, it actually is a very important question because it says something very deep about radiative cooling of the atmosphere, actually. Indeed. So to help you out, I've marked these, and I've copied it onto the next slide with 1, 2, 3, 4, 5, and I'm going to show you where the 1s are, where the 2s are, the 3s, the 4s, and the 5s on this map. And so let's start with the 2 to get you out of your misery. It's the deserts of the world where it doesn't rain. We kind of anticipated that, but it also doesn't cool. And it doesn't cool because there's not much water vapor in the atmosphere, and therefore there's not much downward long-wave radiation. So the biggest player in cooling of the atmosphere is actually not surface temperature and things like that. So it's not OLR, it's the downward long-wave radiation, and that's largely driven by water vapor plus clouds. If you have cloud bases near the surface and large fractions, then you get strong cooling. So we see the strong cooling regions of this Earth. Number 1 are these sort of red regions, the subtropical oceans, mostly. The weak cooling, weak rainfall regions are all where the big deserts are on Earth. And then going from the other end, the strong precipitation regions is our favorite ITZZ. And then there's this intermediate region which has weak cooling and medium rain is number 4. It's these light blue regions. And that's partially, you can see immediately the monsoon regions of the Earth are included in this. My favorite monsoon, the Australian one, but most people's favorite monsoon is the Indian one and Southeast Asian one. So that's also partially a time averaging thing. It's just they will be dark blue for parts of the year and dark red for the other part of the year. And when you average, you get light blue, right? So you have to be a bit careful because this is annual average. But it's quite a revealing map, and then the yellow guys are the strong cooling medium rain, and they connect the strong cooling no rain with the weak cooling rain regions. So it's kind of amazing that you make this two-dimensional histogram, you draw some lines on it, and you plot the points, and they all make sense, right? So we all take that for granted. Just as a quick aside, I think for you guys here, it's probably not a big deal, but everywhere I give this talk, it's a good reminder that OLR is not a good estimate of radiative cooling, because here's OLR, and here's atmospheric cooling. And you can see the reason we get away with our OLR thinking about radiative cooling is that over the tropical, subtropical oceans, it's true, there is a nice relationship between cooling and OLR. But then regions like the deserts, the polar regions, it completely breaks down, because it's all about water vapor in the atmosphere. Okay, that was just an aside. Now here's the first surprise that we got. Here we asked the question, so what if we average the whole tropics, but not over the 10 years, but every day? How close to this balance are the tropics on a daily basis rather than on a 10-year average basis? And I thought there would be 50 watt per meter square deviations. That was sort of my guess when I had to guess what the plot would look like. And it turns out not to be true. It's more like 15 watt per meter square deviations. So much to our surprise, the tropics is very close to this balance between heating and radiative cooling and convective/surface heating. It's very close to it, actually, every day. And it's a big surprise, actually, to me, how close the system is. And the thing that makes it vary, if you look at time series of this, is actually the precipitation, is where all the variability comes from. It doesn't come from sensible heat flux. Tropically averaged is pretty steady. And it also doesn't come from radiative cooling, tropically averaged. It comes from precipitation. So on daily time scales, so these are each data point going into the histogram is a day. There's about 3,500 in our sample. So this nearness to balance, closeness to balance is actually there every day in the tropics. This is not true if you go to small areas, just to talk, we come back to dynamics in a minute. So if this is a 20 by 20 degree area centered near the dateline, and you do the same, you play the same game, you say, oh, what about if I make this histogram in a 20 by 20 degree area? And you can already see it's nothing like an equilibrium. It's completely in this anti-balance mode. When it rains a lot, 400 watts per meter square rain, it doesn't cool much at all. So it's really the dynamics driving the rain, and the cooling follows rather than the other way around. The cooling is not responsible for the rain. I was already very pleased with this plot, as you can imagine, in my anger-driven part of the research, because 500 by 500 kilometer, no way, Jose, right? There's no chance that the atmosphere is in equilibrium. But we'll come back to that. So now let's go a bit into how does it all work, how does it hang together, and what are sort of some really basic fundamentals. And also, how do things change with scale is the next thing to answer. So we have a hint that at smaller scales, it behaves differently from larger scales, and that's fine. So to do this, we simply calculate, we call it a distance from balance, distance from equilibrium, and it's not a rocket science measure. It's simply adding the three terms together at every point in the tropics every day. So we have daily data, we have 1 degree resolution, so at every 1 degree grid point every day. And if you really just take a single grid point on the left, this is the distribution that you get of this distance measure. And it shows something very fundamental about the atmosphere. It shows that most of the time, this again is a point near the dateline. Other points look different, but only quantitatively. Qualitatively, almost all points in the tropics you pick look like this. So most of the time you get a negative departure from balance, which means you are in this cooling state. But it's weak. It's only, it doesn't even have a unit here. It goes down to about 150 watts per meter square, sort of the most cooling you can squeeze out of a column. But when you have a positive deviation, which means the rainfall is completely dominating the balance or the imbalance, you can go up to 2,000 watts per meter square. As you increase the averaging, which goes from left to right, so this is 1 by 1 degree, 10 by 10, 20 by 20, all the way to 90 by 90. Just stick it, we are sticking to the same point, we're increasing the area. This asymmetry disappears because on average the rainfall becomes smaller and smaller, and you end up with a quasi-Gaussian distribution for large areas centered on 0. Most of the points are near balance. That's what we saw in the tropics, right? This asymmetry has fundamental consequences of how this equilibrium must be set up, right? Because if the points that can deviate positively, the rainy points, convecting points, so this rain is all made by convection in the tropics, or most of it, the rainy points can deviate a long way, but the cooling points can't. So there's a lid on the, and that's again comes back to water vapor in the atmosphere and the radiation that follows. We cannot cool a column by much more than 150 watts per meter square, but we can heat it up to 2,000 watts per meter square. So that means for every column that heats, there need to be more columns that cool, right? So if you believe the 2,000, for that one rainfall event here, we need about 10, 15 cooling events, i.e. grid points that cool. So it immediately implies an asymmetry in the area that's covered by precipitation and the area that is cooling effectively, right, which was the subtropical ocean. So you have another reason to understand why the tropical regions that rain are so narrow and the regions of the subtropics are so big. Because it has to be that way, otherwise we couldn't maintain this radiative-convective balance. It wouldn't be possible. All right. So now the next step we took is, what if we wanted to see how many points in time and space are actually in equilibrium? We start in time. How many points in time are in equilibrium as a function of this averaging scale? So we define very generously that we are near balance if it's within 50 watts per meter square, 50. That's a very generous definition, but it takes care of potential measurement errors, which could be large on an instantaneous basis, daily basis, right? So they might not be large on a 10-year average, but on a daily basis, they could be quite large, as well as dynamics. So we allow a little bit of dynamics to happen and still be in what we call balance. So if you do that, just look at the red curve, you get a curve like this. So this is the percentage of times, percentage of days for the red curve, that the system is within 50 watts per meter square of balance as a function of over how much we average. So a single grid point, the number is about 10% of the time you find this balance. So that's not good for the people who run small domain RCE simulations, because small domains are simply not in RCE very often. So it's not a good paradigm for the real world. It's a great paradigm to run models, but it's not a good paradigm for the real world. Even if you go to 1,000 by 1,000 kilometer, that number only goes up to about 30%. And if you want to have 80% of the time, say, in this balanced state, then you have to go to at least 5,000 by 5,000 kilometers, roughly. That's the domain for models to use. And the reason is obvious from all we talked about. You need to be able to establish narrow regions of rain and wide regions of subsidence. Now, if you force a 500-kilometer model to be in this balance, it will have to do the same thing. It will have to make a narrow region of rain and a large. There's one other state it can make, which we'll come back to. All right. Much to our surprise, we said, oh, yeah, OK, but that's because we use daily. What if we time average? But much to our surprise, the time averaging has a relatively small effect. So these different colors are all different time averages. Yellow is a 5-day time average. Green is a 10-day average. Blue is a monthly average. And you know, in the monthly average on small scales, you go from 10% to 30%. That's not exactly massive, is it? And then we have seasonal and annual averages. By the way, this little kink we can explain. Once you average over seasons or annually, the sample size goes down and you get more noise. But also, the point we've chosen here is on the date line, and there's a rainy ITZZ to the north and a rainy southern Pacific convergence zone to the south. So as you go out in your average, you actually get to a point where you include those two rainy regions, and that makes it that destroys the equilibrium, actually, as we know, because the rainy regions themselves are far from equilibrium, far from balance. OK, how does it look at the rest of the world? So this is just the daily time series again, but for different regions on Earth. So there's quite a bit of variability as to how quickly with spatial averaging different regions of Earth reach balance. The worst is the Western Pacific, so you never really get to lots of balance until you take very large averages. Again, makes sense. The Western Pacific is this region where you have this broad warm pooly area that's convecting, not a narrow ITCZ with big subtropics on the side, but this warm pooly region, and then continents to the north and the south, which mess everything up. The regions where we approach it the fastest is the Atlantic. That's also interesting. Very narrow ITCZ, very well-defined subtropics. So you get actually, as you make your spatial average bigger and bigger, you approach the fastest. It's the fastest region of approaching lots and lots of times where it's in equilibrium. And then the other side in between, the curve we looked at so far is the orange one right in the middle of the pack here. Okay. Now comes the next question is, can we say something about the role of organized convection in establishing this balance? All right. So how do we do that? More observations. Now we use observations from ISCIP, the International Satellite Climatology Project. And there's a whole 1-hour seminar hidden in this graph, which I can't give. So for many years, we have been using the ISCIP data to identify from the cloud morphology, basically, or the cloud statistics. It's not really the morphology, but from the statistics of the cloud in a 2.5 by 2.5 degree grid box as to what state the atmosphere might be in. And we've identified 8, which I summarize in 5 here. 8 states that the atmosphere can be in globally. And the states that we can identify, and we've shown this, is organized deep convection. So that will be this sort of pinkish color in this plot, although it doesn't come out as pink. What's with the projector? It makes this look orange. It's most certainly, all right, fair enough. We'll work on this. It's the leftmost column on all these. Non-organized deep convection is red. Congestus convection, so shallower clouds, are orange. Cirrus is yellow, cirrus with no convection attached. And then everything else, green, is all the shallow cloud states. Shallow cumulus, stratocumulus, we just lump them together into shallow suppressed sort of regimes. Okay? Now, we take this 20 by 20 degree area just to start our thinking off, just to introduce the concepts of this. And we ask, okay, if this 20 by 20 degree area is more than minus 100 watts per meter square away from balance, which happens, by the way, 2% of the time, so it's not very often in this particular region that we picked. What is the mixture of these cloud states? And what you see by far, the dominant cloud state is shallow clouds, right? Which is what you would expect. The system cools a lot, but doesn't have any precipitation. So we get these massive differences. As we go to differences of 100 to 50 in the negative, the picture hardly changes. It's a little bit more convection creeps in, but it's mostly still these suppressed states. On the other hand, if we go to large positive excursions from balance, which happen 7% of the time, it's dominated by the 2 convective states, the organized and the disorganized convective state, right? So that's kind of nice. And then when the system is in equilibrium, which in this case happens 40% of the time, then we have this mixture with the predominant state still being the suppressed state, as we kind of would expect, because a large area needs to be covered by that, and then a small frequency of occurrence, about 15% of organized and unorganized deep convection. And quite a bit of congestus as well, by the way. That's about another 15%. So if you want to say how much precipitating convection, it's 30% of the time that we find it. Okay, the next graph, we will look at only this category. So we will say, let's pick this, because that's our special paradigm, that there's balance between cooling and heating. So we're only going to pick this category, but we're going to plot it as a function of averaging scale. And that's kind of a nice summary of what organized convection really does in this problem. So pink, this time it is pink actually. The pink line again was organized convection. I really want you to focus on pink and green. So pink is organized convection and green is suppressed states. And we can see that both of them increase slightly. The others sort of decrease, especially the cirrus, as we go out and averaging. Remember, as we go out and averaging, we're averaging further and further into the subtropics, right? So we start at the equator, then we go 10 by 10, 20 by 20, and so on and so forth. So we include more and more subtropics as we do this averaging. We can only go to 70 by 70 here because we don't have the ISCIP cloud states beyond 30 degrees. or they change once you go beyond 30 degrees. So there's two fascinating things in this plot. Number one is if you're in a really small area, a single grid point, which is the leftmost configuration here, really organized convection is not a player at all. So on small scales, organized convection does not contribute to the few occasions. The black number, by the way, is the percentage that it happens. So about 10% of the time, we only find 10% of the time that we are in balance. But when we are in balance, certainly there's no organized convection to speak of. Makes sense. If there was, on such a small area, it would rain so much you couldn't possibly be in balance. There's also no suppressed, there's also absolute minimum in the suppressed cloud states. That also makes sense, because if they had a big frequency of occurrence, then they would cool more than they would rain, and that wouldn't be in equilibrium. So when you have equilibrium, you really have these disorganized convective states dominating the rainfall, and a bit of cirrus, actually, in the real world. And so from a modeling point of view, there's one other answer these cloud resolving models give occasionally, and that is completely disorganized convection when they have this equilibrium state. But they hate that answer for some reason. But it's the right answer. It's what nature does, right? But that's not what's being studied. What's being studied is this organized state, but that's not what nature does, at least not on those scales. The other fascinating result of this is that if you calculate the ratio of the green line to the pink line as a function of averaging, then you get this blue number at the top here. And you can see once you get to about 30 by 30 degrees, which is roughly where we think, more than half the time we are now in equilibrium, this number doesn't change anymore. So there's an almost constant ratio between suppressed and organized convection, suppressed states and organized convection. We don't have a full explanation for this but it shows the importance of organized convection in this game, because you could imagine the planet doing this with disorganized convection, right? So there's no reason for the convection to be organized to achieve this balance. It could be disorganized all the time. But you'd need a lot of disorganized convection. So one hand-waving hypothesis one could have is that if you wanted to achieve the rainfall that's needed to balance the radiative cooling with disorganized convection, it would take up too much space. And therefore, you need to organize convection. One of the important things that I didn't tell you is that the rainfall in this pink regime is about 2 to 3 times the rainfall in the red regime. So you really get a massive intensification of the rainfall when the convection gets organized. And so you can hypothesize that you need organized convection on the Earth, because otherwise the rain-making disorganized convection would take up too much space, and you couldn't organize within remember that where the subsidence ends on Earth is set by the rotation rate of the planet, and we can't change that. It's dynamically set. So you run out of subtropics at some point, right? Subtropics have to end somewhere because of the rate of the rotation of the Earth. So a few words about models. Don't need my glasses anyway. So first question is, do models have this relationship between cooling and precipitation that real Earth seems to have? And the answer is yes, they do. On the left-hand side, these I got from Penny Ma, are a few AMIP runs. So this is running climate models with prescribed sea surface temperatures, observed sea surface temperatures. Those are the dots, the circles. And then the other set of experiments in this graph, the crosses, are when you switch the convection scheme off altogether, which is very spooky, which is why they call this experiment spooky. No, they came up with a fancy acronym. This is an acronym for something very fancy, but it's very spooky to someone who works on convection that at a 300-kilometer resolution, someone would switch the convection scheme off. It's a very spooky thing to do, but they do it anyway. And you can see if you plot the long wave cooling, in this case only the long wave cooling versus the precipitation on this axis, on this graph, they all fall on this sort of straight line. So that's good news. The models do this cooling to rainfall relationship. But you can immediately see, Christian was talking about at the start, there's these errors in models. They seem to rain too much. Just maybe, this error has nothing to do with what makes the rain and everything to do with what makes the cooling. It's entirely possible. I won't have an answer for you whether that's true, I'm afraid. But it makes you think, right? The other thing that you can see, and I forgot to mention that, is that deserts on Earth reduce the tropical rainfall. I let that set in. It's a fundamental thing that happens on Earth. The presence of deserts reduces the precipitation in the tropics. And you know why now, because the deserts don't cool effectively. So they don't need the precipitation to balance that as much. And here's my evidence, piece of evidence number 2. These are results from so-called aquaplanet experiments. So we remove all the continents, we fix the SSTs to a certain value. And what you see, the rain rates are on the order of 4.5 millimeters when on the real planet. And these are kind of the same models. They are 3.5 millimeters. So you get more rain on an aquaplanet than you get on the real planet. And that's because there's more cooling on an aquaplanet than on the real planet. And you can see that here too. So the mean here is about 220, and the mean here is about 200. So this extra 20 watts per meter square results automatically in extra precipitation. But again, if you take different models, different resolutions, and so on and so forth, with parametrization, without parametrization, you get an almost straight line between rain rate and cooling. So that's kind of reassuring. Then you see this. So if you take this long wave cooling versus precipitation and you plot the observations on it, oops. Now there's an oops, and I think there's a double oops. I think part of this, so the first thing you see is the models need much less cooling to make more precipitation. We'll come back to that. How is that possible? We said this balance has to be obeyed. Somehow the models get it wrong. What's going on? So the models do their rainfall with much less long wave cooling. I think the fact that the rainfall is here has two parts to it. One is the models are wrong, and one is the observations likely underestimate the precipitation a bit. Remember, this is only tropics, so this underestimate that we're talking about is largely in the light rain parts of the tropics. So this GPCP, so we have gut feeling that that's a bit of a low estimate of the true precipitation. But so how do the models do this? So we come back to my favorite histogram. We start with that. So this was our observed histogram of the climatology. This time it's only long wave cooling versus precipitation, but it looks very similar to total cooling. And these are two individual models at the bottom, and the multi-model mean. So this is about 12 or 11, I think, 11 climate models run in AMIP mode with prescribed SSTs. And you can see some fundamental errors in the models. So they all underestimate the frequency of occurrence of points that cool a lot. So they don't have the cooling points as much as the real world has them. They all overestimate, and you can see that most impressively in the individual models, but it's still there in the multi-model average. They all overestimate the rainfall. So they all have this tail over here, where it doesn't cool a lot, but it rains. And I show you this in a map for one model and the multi-model mean. So this is the rainfall error of multi-model mean. And I already said models rain too much in the tropics, and this is what it looks like in a multi-model average mean. And a single model, this happens to be the Max Planck model. Doesn't really matter. It's actually quite a typical model, which is probably why I picked it. This is the long wave cooling error in our models. So this is now starting to become interesting, because we see that where it rains, the models actually cool too much. So the suppressing effect of the high cloudiness that goes with the rainfall, the suppressing of the cooling from that effect is not strong enough in models. And that's true for the multi-model mean as well, although it gets weakened. What doesn't get weakened in any of the in the average is this large underestimate of long wave cooling in the subtropics. I think this is a big deal. We'll come back to that. But then models are smart. Yeah?
Just want to make sure, long wave cooling includes the one reference cloud. So
Yes, it's everything. It's just the net long wave.
one slide, can go back. One slide is so to 200. Go back.
This is only long wave.
Go back.
Go back.
Yeah, here. Long wave cooling is about 200.
Not in the models, it isn't. It's about 200 in the observations. In the models, it's more like 195.
45 here.
Sorry?
Does it include cloud?
Yes, this is everything. Everything. It's just the long wave fluxes. They doesn't take care of what made them.
So you said in the models, if it rains more, the cloud cooling is larger.
Yes.
That does not make sense.
Yeah, it does. It's just wrong. It's an error.
No, it does not. Because if you rain more, maybe you could have a high cloud. High cloud means you have a cloud really forcing the warmth from the atmosphere.
Yes.
And the cooling is much smaller.
Yes.
So if you go back
And the models get that wrong. Yes.
If you go back earlier slide.
No, but let me explain. I mean, the models don't cool enough on average because of the subtropical effect.
Because we all know, I think, because in the tropics, in the convection region, North Pole region, the cloud always have warming effect.
Yes?
Is long wave cooling is much smaller.
Yes?
Cloud effect, and the rainfall is much bigger.
Yes?
Always cloud effect and rainfall effect basically cover.
Yes?
That's why I just don't understand your slide 200.
What's there not to understand? It's just the models are wrong, is what I'm saying. Why can't they be wrong?
Okay.
Do we really believe our models are great?
If you say model right, it's good. Okay, that's fine.
Well, that's the whole point. Yeah, it's the whole point of my arguments. The models are wrong, and they are wrong in another important way, as we will see, as you see on the next one. So they have this, on average here, they actually underestimate the long wave cooling, right? In the rainy regions, they overestimate it. In the non-rainy regions, they underestimate it. Because the non-rainy regions are much bigger than the rainy regions, overall, it's an underestimate of long wave cooling. So they do not cool enough. That's what we saw in these other plots as well. So they're lower than the observations in their cooling. But they compensate very nicely for this by also underestimating the shortwave heating of the atmosphere. Okay, so in the net, they actually average to almost okay cooling of the atmosphere. All right, but they do it by shifting both the shortwave and the long wave in the same direction. And then the net effect doesn't look so bad. So I put these slides in the wrong order, so I'm going to go backwards one. So this is what this looks like if you do these histograms for the Max Planck model, right? So this is the, and the spatial distribution is still wrong. You can see that here. Whilst the total radiative cooling, as I'll show you, is almost the same as what's in the observation, the spatial distribution of it is completely wrong. It's too much cooling in the rainy regions and not enough cooling in the subtropical regions. So going back to this histogram, this is the total cooling. The model cools actually more than the observations in the total, all right? So that explains why it has more rainfall. Okay, it's about a couple of watts per meter square more cooling, and that explains the extra rainfall in the model. But if you look at long wave and short wave separately, but now we will come back to whether this is all models' fault. It could also be observational issues, of course. Once you start splitting things up, things get a bit dicey also in the observations potentially. The model is underestimating the long wave cooling, and it's underestimating the short wave heating. It so happens that it underestimates the long wave cooling by about 5 watts per meter square, and it underestimates the short wave heating by about 8 watts per meter square. So there's 3 watts per meter square. I should have said 6 and 8. So there's this 2 watts per meter square that we see in the total, that it cools too much and therefore makes extra rain. So in these very basic things like tropical average cooling and heating, our models are not very good. And there must be consequences for climate change because the long wave part, so both depend on temperature, because short wave heating depends on water vapor depends on temperature, but the long wave part depends on temperature to the fourth, right? So it's actually, whereas this is a Clausius-Clapeyron effect, yeah, more water vapor, more absorption, but this is there's a temperature to the fourth somewhere in there, or temperature to the third if you take the derivative. So it matters not only how much cooling you have overall, but how you make it will matter to how you respond to a change in temperature. So there's an open question at this point, because I'm also not 100% trusting the data. What happens? What's really funky is if you plot the whole globe and you look at this shortwave heating difference, you can really see the southern hemisphere sticking out. To some extent, it makes sense. We know the models are also not reflective enough over the Southern Ocean and, for instance, over the stratocumulus regions, which you can see here. Models are not reflective enough in those regions, so you don't get the secondary absorption of shortwave radiation from the reflected radiation, right? Because radiation goes straight down into the surface and doesn't come back through the atmosphere a second time. So maybe that's all there is to this. Okay, I'm going to skip this. So I'm just going to summarize what I said. So this balance between heating and cooling is a non-local phenomenon, and it's an interplay between precipitating, non-precipitating regions. Because the cooling heating aren't symmetric, the heating is much larger when it happens than the cooling. This asymmetry has to imply that the precipitation regions must be small and subtropics must be large. That's kind of cool. Downward long wave is key to this whole game, so never ever think that top of the atmosphere radiation tells you everything you need to know. The tropics, and this is kind of has implications if it's really true. If you really believe the tropics are near balance radiation precipitation, and near balance is a few tens of watts per meter squared, 10, 20 maybe. If you're that close to balance every day, then the extratropics must be too. So that's kind of a cool one. I've thrown this over the fence to some extratropical friends of mine and saying, well, if the tropics the globe is in balance, we know that, has to be. Or, well, there could be storage, of course, but close to balance. So if the tropics are close to balance, the extratropics must be too. Well, how does that work? How does the Earth realize that? How does it happen? So that's kind of a cool question. Regions smaller than a few thousand kilometers are almost never in that balance. And when they are, organized convection is absent. So that's bad news for small domain radiative-convective equilibrium modeling. Climate models do not faithfully reproduce this relationship. They produce larger precipitation than observed for lower long-wave cooling rates, not total cooling rates. And they compensate by underestimating the shortwave heating as well. And then I think there are consequences for what happens in their climate change simulations. And that's it. Thank you very much.
Questions? Yeah, I'm Joel. Mike.
Very nice, thank you. So is the overall conclusion about the RCE experiments that in the end, the reason why we get with the models, the organized convection sort of paradigm is just because there's something wrong in the model setup, or they're actually looking at the solutions that are not really interesting from the fact that they don't really look like reality, but they seem to be interesting from an intellectual perspective.
Yes.
But they're just ignoring the other ones that they get. But the reason they get it, is it the large-scale forcing that they create? What's the reason they get those solutions that are unrealistic?
I think the reason they get is, and you know this very well, if you work with models and you don't have certain scales represented in the model, you will alias them into whatever you can resolve. So this model has only 500 by 500 kilometers or 200 by 200 kilometers often to make this equilibrium. So it will make it in a quasi-realistic way, right? So the model will make this organized convection. And I actually think so, and it's done through radiative feedbacks, radiation circulation feedbacks. And I think we know that those radiation circulation feedbacks in the real Earth are very important for the ITZZ as a sort of monthly mean phenomenon. And so all that happens is the spatial and temporal scales of ITZZ organization get aliased into a model of 200 by 200 kilometers. That's what happens. And the model has no choice but to do this. There's the other solution, but it's kind of hard to achieve, I think, this bubbly convection with a little bit of rain here and there. Because the moment you get real deep convection, it might be important for the real world as well, as we discussed. The moment you get really deep convection, you also get lots of cirrus clouds, and the cooling stops, right? So then you have to compensate by far field effects.
Yeah, it's very interesting talk, but you largely focus on the tropics,
Yes.
which is plus minus 30 degrees. And so you are not talking about the rain outside. We are not in the tropics. We're 34 degrees here. And I was wondering, things like convective radiative-convective balance. There's thunderstorms in mid-latitude. And so I was wondering how important are those mid-latitude thunderstorms in your study?
Well, so we were kind of fascinated to see that the tropics seems to achieve this balance on its own. It doesn't really need the extratropics to do it. So that's just a result, right? We didn't necessarily expect that. So extratropical thunderstorms are not important to achieving the balance. They are definitely, I'm sure, definitely important for the global balance. But we can now, what we postulate is you can look at this global balance almost as three parts. There's the tropics, which is in balance by itself. Then the northern hemisphere extratropics and the southern hemisphere extratropics also must be in balance by themselves. And I've looked at whether that's true. The answer, yes, it is. But how it works, no one's looked at yet. And what the role of fronts versus isolated thunderstorms and so on is. But it's similar. A similar story will emerge. We will have these narrow regions of rainfall, right, which are fronts, which tend to be narrow. We'll have thunderstorms and wide regions of suppressed conditions to make the cooling. It will be the same answer in that sense.
Can you say something about the latent heat for the balance? I mean, on the other hand, the evaporation and precipitation must be equal, right? So
yes, that's right. So
is it just the latent heat driven by precipitation?
So no, you're absolutely right. So there's one assumption in here which may not hold at relatively short timescales in relatively small areas, and that is we assume that precipitation and evaporation are the same, right? Because we think we have better observations of precipitation than evaporation. And over long periods, that may be a sensible assumption, but over short, it might not. Is that what you're referring to?
Yeah, but like just in general, right? I mean, shouldn't the precipitation be also constrained by the latent heat release?
No, because they are the same in the long term. In the long-term average, precipitation and evaporation are the same. That's the water balance of the planet, right?
Yes, but...
So if they are the same, you can use either in this analysis. Okay. If they are not the same, you can't.
Yeah, and then two more at the front here, and then we'll be...
Okay.
Then we'll call quick lunch.
Yeah, I think I'd like your first conclusion, radiative-convective equilibrium is a non-local effect.
Yes.
I think when I was a grad student, I worked with Ramanathan, we published paper. I think we look at the heat budget in the Western Pacific warm pool, and especially emphasize the dynamic role, because it's radiation, convective, and convection dynamic balance. You have to consider dynamic heat transport.
That's right.
Which in the Western Pacific warm pool, or ITCC, dynamics is a heat sink transport and from this to the subtropics. But in subtropics, dynamic is heat source.
Yes.
So you have to look at the radiative dynamic. Radiative probably tropical wholly or globally it is, but locally it's not.
That's correct.
Yeah, I really like that conclusion. Second, I think you mentioned the downward heat flux is a dominant term for the radiative cooling. I think in my paper 2002, we look at the cloud radiative forcing, what we referring, and clear so is the downward heat flux is very important for the annual radiative cooling.
Yes.
Yeah. I really like those two conclusions.
Thank you.
That makes sense. We have published paper already.
Yeah. So the agent that makes all this hang together is the circulation. I should have said that somewhere in the talk, and I didn't, right? So the agent that makes all this argument hang together is the circulation. It's the dynamics, what you call the dynamics. Yeah.
Thank you for a very interesting talk. So I understand you said the total model bias in long-wave and short-wave, including both clouds and water vapor effect. So I wonder if you look at which one is a clear sky water vapor or is a cloud makes the most errors?
The short answer is no, we haven't looked. We have the modeling stuff we've only looked at very recently. And yeah, it's... And there's also, I will say this because it's really important, and that's why we haven't written any of the modeling stuff up yet. There is a question mark about how good are the observations as well. So once you start separating into long wave and short wave, you have to be pretty sure that your observations can do this. We use tropical averages, right, and long-term averages, but still, So I would like to repeat this with other data sets, which there are a few data sets that have estimated surface radiative fluxes, so you can calculate the cooling.
Quickly. So you're suggesting, but very interesting talk. You're suggesting that there is not much heat exchange powered, but we know that the oceans are carrying a lot of heat powered.
Yes.
Okay.
So I'm not suggesting that. I'm suggesting that that's a small term compared to the balance, to the terms that make the balance.
Yeah.
I'm not saying it's zero. Actually, if you
maybe the 3%.
If you take the 3 watts per meter square and multiply it with the area of the tropics, right, with the meter squares of the tropics, you're probably very close to the petawatts that of transport that we would expect.
And another quick one. So if the subtropics are moving forward with climate warming, that means the precipitation should get more intense.
Well, so there's a cool one here. It's if you want to squeeze. So if we know we are squeezing out more rain in a future climate, right, 3% per degree, then this has I think you can think of it in both directions. These are balance arguments. Balance arguments never explain anything. Right? They're not causal. They're basically constraints. That's why the talk's called a constraint. So the atmosphere, somehow, this constraint has to be fulfilled. So if you have more rain, you can either expand the regions that cool, which would be an expansion of the subtropics, or you could increase the intensity of the rainfall without changing any of the areas. Both are possible, right? And so it's not clear to me. I'm confused about this whole subtropical expansion discussion, because in Dynamics 101, I learned the edge of the subtropics is set by the rotation rate of the Earth, because that's how far the parcel can go before it gets deflected, right?
Yeah, but it also depends on the flow, the outflow at the level, how strong it is.
Yeah, I understand it's not black and white, and it's not just one thing. But there's an interesting question around climate change from just this balance argument. So if you have to rain more, and you expand the rainy area, then you also have to expand the cooling area. Or you don't do that, and you just make the rainfall more intense where it happens. Yeah. So which of the two it is, we'll see. But it has to be one of the two or a combination of the two.
And there's even hypotheses about the rain areas contracting, being more intense. So, in other words, we haven't got a bloody clue. That's what it means.
That's kind of right.
There's no theory as yet for this to drive us to understand. So it's a lot of interesting research for all you young folks there. You can solve this problem.
That's right. But we go and play golf, right?
Yeah,
or something like that.
Not today, though. Okay.
All right.
Let's just thank Christian again. Yeah, okay. And Christian's around for the rest of the day. He has a kind of a schedule, but if anyone who wants to talk to him, I think we have possibly a window of time. When's he doing the tour? Do we use it? Now, okay. We have a window of time at about 2 o'clock.
Or come to lunch.
Or come to lunch with us at 12 in the CAF. Meet us in the CAF, which some people are doing.
CAF, is that what it's called?
Yeah. 167.
The CAF.
Yeah. Okay, thanks, folks. Thanks for braving the weather.